Welcome to Switching the Engine, getting some insights into what makes Kubernetes run, or at least from the DNS perspective. Or else, I mean, you all want to go to the after party, so we won't dive into everything. So who are we? I'm Michael. I'm a maintainer at CoreDNS. I'm running an open source research lab called Okkur, and also support companies via Rucker solutions focusing on Kubernetes, Google Cloud, CoreDNS, and with things such as Git-based DNS.
And my name is Jake Sanders. I'm a software engineer working on security in GKE here in Seattle.
So let's dive into our agenda. We first want to give a bit of background. I know there are a lot of, or a few talks already around CoreDNS, but we want to set the stage on what we are actually talking about. Then we will dive into a new cluster add-on, which is called NodeLocal, which will cache a bit more inside the cluster. Then we have a few benchmarks. We go step by step. So we will look into some local benchmarks, and then into cluster benchmarks, and then we have one example application, which is anecdotal on what might happen with a switch and in general what you can do with an actual application in a real-world scenario. The next one is basically the outlook, so what will happen with CoreDNS and basically CoreDNS and Kubernetes as in the future. So basically the background, the primary use for DNS with Kubernetes is service discovery, as you all know. It's basically gluing everything together. So there's the internal use and the external use. We will focus a bit on the external use case, especially on our end-to-end tests. But everybody knows like DNS is the address book of the internet. So it's connecting to databases, request remote files, send email, and stuff like that. So let's dive a bit deeper into the history. So we had Kube-DNS before. And just to prevent the confusion, the DNS service inside of Kubernetes will still be called Kube-DNS, but it will be switched out with CoreDNS. So what is Kube-DNS, or what was the old way of doing things? It was a bundle made up of DNS mask, which is used as a resolver locally on a lot of Linux distributions, and as a cache. Kube-DNS was using it as a cache and bundled it together with SkyDNS. It is a Go-written DNS server, and it was written by Meek and a few other people. So let's dive into what's CoreDNS. So basically the new way of doing things, the actual default way since 1.13. So it's a great foundation from a design perspective. It builds on a good ecosystem. It's building up on Caddy, which is a Go-written web server. It has a lot of extensibility due to being based on a middleware and plugin-based system. So the cache, for example, is one plugin. We have metrics, Prometheus metrics built in, and also the Kubernetes API is just one plugin of many. So why was it built and built again by Meek Gibbon? So anecdotally, he wanted to run or wanted to have more metrics inside of his DNS server, which was at that time a bind-based one. So adding a new feature to bind seemed to be really, really difficult. So instead, he started a new DNS server from scratch. I mean, that's what you do when you want to have nice-looking stats, right?
We've all thought it.
So let's dive into the different protocols that are supported. So CoreDNS doesn't just support the base DNS protocols. One is basically UDP, was what the first iteration, it's lossy, and that basically gives a bit of problems down the road. The next iteration was TCP. It already has connection. It's a much better protocol for reliability reasons. And we have two modern ones that are actually specified already. So they have a specification, and they're used in production. The first one is DNS over TLS. So it basically encrypts all your traffic, so it's a bit more private, secure, and it isn't fiddled with in the path in between. The second one is DNS over HTTPS, which is used, for example, or can be used by Google's public DNS or Cloudflare. Firefox recently switched to using it by default to provide better privacy and encryption. And one reason why it's providing better privacy is it's using the default 443 port, and therefore it mixes DNS traffic and normal web traffic, so you can't see which, you can't tell the difference. The next one is GRPC, which isn't specified yet. It's a proof of concept, you could say, and we will see how that helps in the future.
So in addition to becoming the default cluster name server in 1.13, another feature related to CoreDNS was also introduced. This time it is actually NodeLocal caching, which will go on to solve many problems for you guys, hopefully. So if you leave here feeling like your day is made, please thank Pavitra Ramesh. She did the job of going through the whole KEP process, iterating on the design, merging the pull requests, getting this to you guys. So it's all about community, and she is one of them. So just some background info on the problem itself. DNS is really a child of the 80s and 70s and 80s, and there are lots of things that date it as such. I'd like to take you on a journey through time, back to the time when the internet was just a bunch of telephones kind of yelling at each other. The phones kind of sucked. Most of the things they talk about were stuff like TPS reports and nuclear codes, nothing too interesting. And there weren't really any sort of high performance, latency sensitive applications available yet. And, most addresses didn't really change all that often. So all of the decisions made back then actually made a lot of sense at the time, but time's arrow moves ever forward, and so do the requirements of this critical abstraction. Case in point, Kubernetes. Adoption kind of took off, and some old decisions have not scaled to modern uses. For example, in the original DNS RFCs 1034 and 1035, they specify the implementation should generally try and prioritize overall network load over performance or availability, meaning that UDP should be preferred over connection-based schemes like TCP, and that retransmission intervals should be generous. And I'm sure that there are several people out there that see that 5 seconds and get just a little triggered, because that is actually a very common thing, and that's part of the impetus behind this change. Speaking of the 70s and 80s, Unix and libc followed the recommendations of the specification very faithfully, and the rest is kind of history. Many clients will still directly or indirectly depend on libc or its behavior. It'll depend on the specification or defaults of the resolver configuration. So these decisions have really propagated to the present day. But even when DNS clients have the ability to force DNS over TCP, that configuration may not be easily configurable at runtime. So practically speaking, many applications are just going to be susceptible to these, timeouts on failed lookups, and especially unlucky victims might have to retry over and over and over and over, and just, very bad tail latencies. These matters are severely aggravated by the way that Kubernetes services are implemented, including the cluster DNS itself. When cluster IPs are resolved to a specific pod IP, the NetFilter suite's conntrack table becomes a critical bottleneck and single point of failure for lookups directed to the cluster DNS, those that are cluster local addresses. This is partly due to the fact that Linux installations normally limit the maximum number of entries in this conntrack table to something that might be classically reasonable back when a mega or a gigabyte was unthinkable. Usually 2 to the 16. And then once that limit is reached, extra packets are just simply dropped on the floor. So if you ever run into this situation, you're definitely going to want to look in your kernel logs and see if you have one of these NetFilter tablefuls, packet loss, that kind of thing. Also, unlike TCP, UDP is connectionless and doesn't explicitly close a connection, which means that contract entries for UDP connections get persisted for way longer than they're normally useful. And furthermore, there are races in the kernel itself, in the code that actually generates these DNAT entries to route packets to and from individual pods in the service. This causes contention if there are simultaneous requests from the same IP and port, resulting in one or more packets being dropped that way as well, even independent of the table itself being full. Unfortunately, many clients will also parallelize the DNS requests for separate record types, such as those for IPv4 and IPv6. And then finally, if you have a bunch of entries configured in your search path, as is often the case in our pods, failed lookups will keep looking up, down every entry in the search path. So every time you search for a domain that doesn't exist, you end up with a multiplicity of these entries that are just garbage. What this all means practically is that you as a service owner are left holding the bag for opaque failures that often completely defy debugging. Drop packets and DNS timeouts usually happen way down at the bottom of the stack, in the kernel itself, and are often obscured by higher level programming abstractions. If you don't really know about these default behaviors and implementation details, you're liable to end up on a bunch of wild goose chases and setting off pagers and just not having a good time. But I'd also like to know that this isn't a problem that's specific to Kubernetes. It's actually existed in the wild for quite a while, very often for other previous implementations of DNSs for exactly the same reasons. And I guess there's, now's the time. But I have good news, guys and gals and non-binary pals. The future is now. A NodeLocal cache is the minimal instance of CoreDNS, which gets instantiated on each node that acts as not just a cache, but also a TCP forwarding proxy to both the cluster DNS and public name servers. This, like I said, this is an optional feature that was introduced in 1.13 at the same time that CoreDNS was made the default name server, cluster name server. So particularly adventurous souls can take the plunge at their earliest convenience, because I know all of you always run at edge all the time. By leveraging TCP, persisting the connection, and avoiding conntrack altogether for connections between pods on a node and the NodeLocal cache, pretty much all of these issues related to conntrack entries and packet losses are avoided or completely eliminated. And as a bonus, all of the other advantages associated with CoreDNS are available, including NodeLocal DNS metrics. So here's just like a diagram of how the request flow works with a NodeLocal cache. Request from a client pod will go into the cache, and either a cache hit will happen or a cache miss. And on the event of a cache miss, the request will either be routed to the cluster DNS or to your favorite public name server that is specified in the resolver configuration, in whatever way you have done so. But just as a sanity check, just to prove that this actually works, let's go through a few benchmarks. Just for this first one, I created this load generator that just basically looked up normal A records for like the 10,000 most popular websites, kind of a toy application, but I also used the TC utility in order to drop packets at a certain rate and just like observe the effect that it had on lookups just between localhost and the public name server. As you can see, UDP is just like slightly more performant than TCP in ideal conditions, but as soon as network chop starts happening, UDP rapidly falls behind, and you rapidly start seeing longer average latencies and huge tail latency. And if you're a service owner that cares about P99, you got to have those 9s. This is going to ruin your day because you're just not going to get them. As you can see, if you only need 99% availability, then you're okay until 1% of packets just go missing, I guess. But additionally, even if you aren't having a ton of packet loss, you can see that TCP connections will generally have more consistently lower latencies than UDP, which is just sort of a bit more unpredictable. On to cluster DNS benchmarking, and this is another huge thanks to Chris O'Haver from Infoblox, who actually did this work when CoreDNS was made available in 1.11 in order to verify that it was a good solution for the cluster DNS itself. What he did was he ran the normal Kubernetes scaling benchmarks that happen when you integrate a PR. With several thousand clusters, going up to over 100,000 clusters or pods and services, and then also added the memory delta that was observed when hitting both CoreDNS and KubeDNS at their highest QPS. So in effect, you can see that under high strain and in large clusters, CoreDNS will always have a lower baseline overhead, and the amount of memory that it consumes will also grow at a slightly lower rate than KubeDNS. So in this regard, it's just like a strictly better alternative. And not only does it grow at a lower rate, it only requires a single pod rather than the 3 or more pods that Kube-DNS has or requires currently. Additionally, the amount of requests that CoreDNS can actually serve is roughly comparable to Kube-DNS for cluster internal lookups. It's just like 10% less QPS available for cluster internal, but similar latencies. However, for cluster external lookups, you can see that CoreDNS has a nearly 3 times advantage in both QPS and in latency.
Okay, so let's jump into the application. So local benchmarks and cluster benchmarks in terms are really interesting, but I mean, what we all care about is the application itself. So how would that affect a specific application? To basically set the stage for a real-world benchmark, which needs a lot of traffic. So we needed to find a nice project or application that actually needs a lot of requests. So let's look into what we use. So our application is TXTDirect, which is a DNS-based redirect engine, which stores basically all the data for each redirect in a text record in your name server or in your domain registrar, and basically enables you to keep the control of your entry point and your data. What that basically makes happen is that the instance that does the redirect is completely stateless. On the other hand, for each request, there will also be a request to DNS to fetch the data. This can be cached, so it's not that problematic, but it gives us the ability to basically get a lot of DNS requests from one single application, which also sort of is more in the real-world application space. So TXTDirect is open source based. It's based on Caddy, so it's just a simple plugin, and we're trying to enable you to run your own redirect or vanity URL shortener. So let's look into how the request flow for TXTDirect works. So we're a Kubernetes fan, so Kubernetes, we look up kubernetes.opensourcesoftware.rocks because we know that's true. So we enter that in the browser. As always, the browser would look up, okay, which server do we actually need to contact for that? So it will look up an A or C name record for kubernetes.opensourcesoftware.rocks. And then the request comes into the instance, the TXTDirect instance, which is by default, as we said, completely stateless. So where does the data come from? It actually uses the model of the underscore, which is used for services usually, so it doesn't collide with like a redirect subdomain or something. So the instance looks up a text record on underscore redirect.kubernetes.opensourcesoftware.rocks. And we see an example of how such a record would look. So we basically have a version to make it backwards compatible. The type, which is host. So that's just the easiest type that might happen. It's usually used to redirect the root of such as example.com to some subdomain, which can then be linked to a CNAME. So that some providers solve that differently, which isn't conformant with the standard. It's sometimes called like an A name record, where they do that on the fly. But we're conformant with the text, basically with the DNS standard. So now that everything happened, it will be a transparent redirect to kubernetes.io. So let's see what the different setups are. So we want to test different things. So we first want to compare what's the performance or real-world performance for Kube-DNS, so that we have the old data, basically. So Kube-DNS, what we do is basically TXTDirect, which is running in the cluster. So we use all the different cluster services. So we're using a service IP. We have the overhead of a pod. We have all the overheads you would have running an application inside of Kubernetes. So that might make it much more usable for you as like an anecdotal benchmark. So what happens before, or what happened before with Kube-DNS, the application would send a UDP request over the wire, so it might run into packet drops, to Kube-DNS, which then does a request to the upstream DNS server. In our case, we just use the Google public one, but usually it depends on your cloud provider. It could be etcd resolve that gets asked, or your company DNS resolver, whatever fits. So the new way of doing things, as we've learned, is using CoreDNS inside your cluster. So we're still sending UDP over the wire, so we still have a lossy connection. It upgrades and it has a cache, so that's similar, but we learn it has better performance, and we will see that in the benchmarks later. Where it gets interesting is the cluster add-on, NodeLocal. So we wanted to test a few things. Here, we are basically sending UDP, so your application still doesn't need to know about TCP-based DNS or any upgrade of protocols. It can basically be a legacy application only supporting DNS on UDP. But the difference here is it's running as a Daemonset on your specific host. So UDP only goes over localhost, which is usually not as lossy as your cloud provider. So there are two different modes to that. NodeLocal can cache or it can't, or it doesn't cache. So in this case, we test both. But what it always does is it upgrades the connection to TCP. And the good thing about having or controlling both the client and the server, which in both cases is CoreDNS, the NodeLocal one is just a bit more minimalistic, is that we can reuse connections. So instead of opening one connection per request, we will just open a few and reuse these, so the TCP overhead is almost minimal. So what else can we do? So what happens in big clusters is you have your usual 5,000 server cluster as you all are running, hopefully. So what happens is that you have 2 or 3 nodes that actually host the CoreDNS instance. And all the external requests go to these cluster servers and then spam your upstream DNS server from 1 or 2 single IPs, which could result, which actually happened in our case, we spammed Google public DNS as much that they basically blocked us. So that results really in a lot of dropped packets, so we don't want to do that again. So NodeLocal has the option to split traffic between internal and cluster external, and basically sending all the internal traffic still to the central CoreDNS instance, but every external request is directly routed from the node where it was created to the upstream DNS server, basically spreading out your external DNS lookups over the whole cluster, which makes it much, much more reliable and much, much more performant. And the last thing, because that's all good and well, but inducing failure is always great, and having a bit of chaos in benchmarks is always awesome. So we had a really reliable network, so we ran on GKE, just as a side note, which we tried to induce a lot, like with running through multiple services or something, but there were just not enough UDP drop packets. So we had a small gremlin that might actually happen that it's in your network already, or in your cloud provider, and it's dropping packets happily without actually you having to deploy something extra. So we deployed it, and it did a small rate of drop packets, I'm sorry. And basically, we send from the application over the wire UDP, and then dropped around 1% of package or 0.5% of packet, and then moved into CoreDNS. So now we know what the setup was, but what's the results? Like, we want to know what were the numbers. So as you can see here, we have 6 different setups. The first one in blue is the UDP over the wire with Kube-DNS. So it has decent performance and not a lot of tail latency. We will have a tail latency graph later, which basically gives you a bit better understanding of what tail latency might make or might happen to your application. The second one in red is basically the new setup for you, which is using CoreDNS as the central DNS instance. And we see a lot better performance. So we're already upgrading your DNS by default to be more performant and more reliable. And now we enter the NodeLocal setups. So what is actually deployed when you use the cluster NodeLocal cluster add-on right now with 1.13, it will cache automatically. It will send all internal traffic to CoreDNS, and then will spread out the load of all external cluster requests right on your nodes. So it will use the configuration on etc slash hosts, resolve to basically figure out which upstream provider to use. In the different cloud providers, that's usually like an internal cluster DNS, so that's pretty fast. So we can see we're adding with NodeLocal, we're adding a new application. We inject something in the path, so we have a bit worse performance without a cache. We're still upgrading the connection, so we make it a bit more reliable, but we add latency. So we can see in yellow that the performance is not as decent as before. We are actually a bit worse than Kube-DNS. So with the cache, that improves dramatically. And if we now look at the orange one, which is adding a cache and spreading out the load, we are much, much faster overall. Interesting enough, because we're looking at
nothing.
All right. So because we're looking at the performance, UDP drop packets won't yet show up. So our graph for the chaos doesn't really show anything interesting. But if we look at the tail latency, we can see the difference. So the teal color is basically our chaos drop packets. So we can see that a lot of tail latency is added. And we can completely remove that tail latency by using a local cache, either NodeLocal or just upgrading the connection. So if you have problems with that, that might be the solution for you. And we can see and talk about what happens with that after the talk. And let's dive into what that basically means, not just from a numbers perspective, but as what we learned from basically this whole exercise. So we have to say it always depends on your specific use case. So is it only internal traffic? Is it only external lookups? What's your latency need? Do you really need that tail latency gone, or is it something that you don't care about? So your mileage may vary. So a nice thing that also came up in the benchmarks was that the search path, as we said, amplifies a lot of bad behavior. So our application connects to a DNS server, and it was speaking to the DNS server of a local host name. So we didn't use the local IP address, we used localhost. What happens was, with Go and Alpine, by default, it doesn't look at etcd hosts, and therefore doesn't resolve the localhost within the pod. What happens is, on each request, it wasn't just our request that we wanted to happen, and we're sending 1 million requests in like 10 minutes. We were seeing about 6 million more. And we're like, okay, something is wrong here. Let's deep dive, and we actually found it out with TCP dump. So what happened was that localhost wasn't resolved in the pod, so it basically tried the whole search path. So it wasn't just one request that was failing, it was 6 different ones that were failing. And in our case, we were still using Kube-DNS as the central cluster server, which doesn't cache negative lookups. So basically, we were hitting uncached 6 million queries on the central one. With that resolved, we basically learned don't use localhost as a name, or if you do and use generally DNS lookups, always add a dot at the end if you know it's an absolute one, because you will never go into the search path. So basically, the negative caching is fixed by CoreDNS because we now actually cache negative responses. So that won't happen that extremely. So what's the outlook? So we talked about the history. We talked about the really nitty-gritty of results and benchmarks. But what might be next? So gRPC, which is hopefully native, so the idea is instead of just wrapping the normal DNS packets inside of like a gRPC piece, we might actually have a DNS native gRPC or DNS over gRPC. It adds a lot of things, and one thing that might happen because of it is watch-based DNS. So instead of requesting or prefetching a lot of cached records, you will just say, okay, I care about example.com because that's a really important domain for me. And it will just watch on that and get the changes instead of looking it up over and over again. So completely removing idle traffic from your cluster. Also performance and reliability improvements, as we always try. And then we hope for any ideas on plugins that you would like to have, on any problems you had running CoreDNS or Kube-DNS, and things like that you want to try out and you might be happy to try out, such as AutoPath and stuff like that. So thank you, and a special thanks to my team from Okkur Labs, which helped me with a lot of the performance benchmarks, and a special shout out to Erfan. Thank you. Are there any questions?
I think there's like microphones in the aisle if you guys want to fight over them.
I got a question. Linux kernel already has a mechanism. The Linux kernel already has a mechanism to do name server switching to an NS switch. Why didn't you make your NodeLocal a name server switch kernel? Why did you use an NS switch?
So relying on something being in the kernel, when you have virtualized stuff on top, is problematic, especially if you consider not just having containers, which share the kernel, but having VMs running, for example, which don't share the kernel, then you're, for example, out of luck. The other thing is that NS switch, for example, doesn't work with Alpine because they don't care about the file. So that is another problem that might be happening. And we have a lot more control over iterating on protocols, doing cache, and adding a lot more features. So one opportunity would be that the NodeLocal cache actually talks to the API server on a watch-based basis. So we completely remove the need to go on TCP or UDP on the DNS requests.
You're essentially, you're bypassing the NS switch. That's what you're ignoring too, right?
So if we're ignoring, sorry, to repeat the question. So if we ignore NS switch, so it depends on the case. NS switch is by default ignored on Alpine. So if you run Alpine-based images, that's by default ignored.
Well, I mean, if something's broken, you don't,
It's a different level of,
Yeah, question. This is some cool stuff that you've done. The numbers are really interesting. Have you considered making your test harness reproducible so that it could be run as part of the CI?
I mean, we've published the code to one of my GitHub repos. So if you guys want to go and try and reproduce it yourselves, I mean, obviously you're going to have to want to spend the credits on GKE, you know, by all means. But like, essentially what we're doing is we're just we're trying to replicate a master. We're having we're spinning up a fake master that has our DNS of choice in there. So hopefully the actual cluster version wouldn't actually affect the results of the test. But yeah, essentially, I think, let me see if there's a slide for it.
Also, we have to differentiate. So Chris O'Hare, for example, he already did use the CI system, so the cluster scaling tests to get the resource usage and basically the effect already running. We could do that all the time. I think that might actually be planned. I have no complete idea on that. Our anecdotal end-to-end test or application benchmark isn't that helpful running on a persistent basis because it's really opinionated on a specific setup. So we ran, for example, 10,000 different domains and therefore didn't have a lot of caching involved, even with a million queries being run. So if you're just having like a hot path of like 10 domains that need to be cached, and that's always in your cache, you will see completely different performance. So that I would feel that wouldn't make sense in that regard. Any other questions? Let's do the mic first.
Hey. Sorry, just 1 second. If you have any questions about the test setup, you can go ahead and email me or tweet at us and stuff like that, and we'll answer your questions.
So I think one of the things you mentioned during the talk was you had a hard time detecting drop packets in the cloud. And my feeling is that that's just going to be the norm. I mean, UDP packet loss in a LAN isn't going to be that high. So do you think you guys are trying to solve a problem that doesn't exist or is minimal, at least in the Kubernetes cluster?
I mean, I could also just like send out a bunch of links to, enumerable like Stack Overflow, Server Overflow, GitHub issues on Kubernetes and then other DNS things. Like this is a relatively common issue that, does get attention. And there is interest in the community for this specific kind of solution for Kubernetes.
Yeah, I totally second that. So we have their production cluster that run into that problem multiple times. And all over, so it doesn't matter on cluster size, it doesn't matter on cloud. There are some cloud providers that drop less packets and basically are completely reliable, but there are also on-prem settings, or if you don't configure any TCP upgrades and you're actually sending the DNS requests over the internet, the average UDP drop rate is up from like 1% to like up to 15%, depending where the upstream DNS server is. So relying on a network that is reliable is not a recommendation from our side, I would say.
It's also worth reminding people that like conntrack was also a huge issue. You can configure the size of this table, but it's not like an actual solution for like some of the reasons described. The races are another one. I was made aware that there at least a couple patches have gone into, or either gone into the kernel or are pending merging into the kernel that solve at least a couple of these data races that would result in drop packets, but that has not launched yet. And I literally found out about it like 2 days ago, so I didn't have really enough time to research it in depth at all. But yeah, so it's not just like the actual network itself. There are more fundamental issues in the kernel that with certain workloads will effectively look like a choppy network.
So we're a bit over time. Let's do one last question, if that's right, and then you can come over and ask questions in private. And yeah.
Yeah, just before I have my question about your mention on the local network, there is no UDP loss of packets. On Pablos.book.com, we run bare metal in around 50,000 systems across many data centers. We have like huge number of switches, and I can tell you from our experience, there is a UDP packet loss on the local network, and the network, as you said, is not very much reliable. My question. I'm interested to know what was the major cause. You notice a latency up to 5 seconds when you have 1% drop of packets for UDP versus TCP. It was because of the timeout on the resolve conf, or because something else? Or because TCP is faster, retransmit and yada yada? Yeah,
so basically just in the sort of toy benchmarks that I had from localhost to the public resolver, this mean latency was entirely tail latency. I sort of debated whether or not to include the median latency in here, and you would see that the median latency is like right around 38 and 37 for each one, with UDP being like a fraction of a millisecond faster. So it didn't really change that. Yeah, all of this mean latency is the size of that 5-second bucket. Yeah.
So if you decrease the timeout on resolve conf, you don't have latency up to 5 seconds.
Yeah, so I mean, one way that people have tried to solve this problem is by reconfiguring the timeout down to like a second or something. It's outside of spec, so you may go ahead and do that at your own discretion, but hopefully this is a more permanent, workable, maintainable solution.
Yeah, thank you.
Thank you, and have fun at the after party, and hopefully there might be drinks.